Hello again. So today let's look at a fully balanced mixer used as an attenuator. For now, please ignore what's written on the right hand side with a lot of mathematics there. But let's focus on the image over here first, the drawing, and look at this particular construction where we have a local oscillator driving one end of the mixer input, and you have another normally driven by the RF signal on the right, the two transformers. Then you pick up the IF as a product of LO and RF. There are a lot of videos and books on how a mixer works, so I'm not going into the details about a fully balanced mixer configuration and so on, but we'll look into one aspect of the fully balanced mixer, which is not used as a mixer in this case, but used really as an attenuator. So we have only one signal here, one RF signal or one AC signal, and the other signal is actually a DC current over here, which is fed into the IF ports. On the other side, on the RF side, we actually have a load connection, or you could leave it open just for demonstration purposes. But typically there will be some load and usually terminated. So let's see what happens when you have a DC current that flows into the IF port. So you have, let's say the current is flowing up into this node. So you have a current that flows into the winding of this transformer and going up and splitting over here. And one part goes through over here to this diode, which is circled in black, and then enters here on the other transformer, and then to the mid tap winding it goes back to the IF. And the other signal that is split goes up through this diode on top and then returns through the center tap again to the same IF node, the lower IF node. So this is basically a simple construction using a single LO signal, which you can of course vary in amplitude, and you want to see what happens, what you get at the RF side. So typically when you have nothing over here, you'll have perfect isolation from LO to RF. That means there is no, if you have an applied local oscillator signal here, you will not see any significant RF signal. It will be very, very highly attenuated, or the minus 50, 100 dB, whatever, depending on how much nonlinearity there is in this particular structure here for the fully balanced mixer, symmetry and nonlinearity. So, but by adding a current, you are actually modifying the properties of this mixer, creating some shifts in the operating points in the diodes which are used, and that will cause some leakage from LO to RF, and that's what we are trying to study over here. So if you look at the right side of this board, you'll see there's a classical Shockley diode equation, which is ID, which is diode current as a function of time, is equal to IS, saturation current, times, in the brackets, e to the power Vd, which is a diode voltage, and then divided by eta Vt, where eta is an ideality factor, and Vt is the thermal voltage, which is Kt over Q minus 1. So this is the entire equation here. And when you apply IDC, you're going to shift this V diode, which is VDT, due to the DC current in the diode. So that essentially causes a VDC voltage. We have to find what that VDC voltage is. And then therefore V0T actually is a sum of the local oscillator voltage in this particular case plus VDC. It's applied across these diodes. There may be a factor of 2 here because of the splitting, but let's assume it's just VDC and IDC. And if you assume that the VLO, the local oscillator signal, AC signal, is much smaller than VT, in that case then you can combine 1 and 2 and you get e to the power, for this term VDT, you can write that as V e to the power VLO plus VDC from here, divided by eta Vt, which, and then expanding by Taylor series, you get approximately this equal to e to the power VDC over eta Vt, and then brackets 1 plus VLO over eta Vt plus higher order terms, which you ignore for now. So that's a simplified version of this particular term over here. So then you can substitute this particular term over here into this one, so you get ID is approximately equal to IS times e to the power VDC over eta Vt times 1 plus VLO over eta Vt minus 1, and that essentially becomes this over here. And then for large VDC, if VDC is much larger than for large VDC, which implies that EVDC over eta Vt is much greater than 1, you will get you can basically ignore the 1 over here, and you get the IS e to the power VDC over eta Vt plus IS times e to the power VDC over eta Vt times VLO over eta Vt. So this portion over here has no time varying component in it, it's the DC component, and here because of the VLO you have the AC component in this part of the equation. So total current ID then is equal to this plus that. Alright, from last page we have this expression we got, the I diode current is equal to the DC component of the I diode current plus IS times e to the power VDC over NVT, eta Vt times VLO as a function of t divided by eta Vt, and that's the AC portion of the current. Now the conductance of the diode is actually equal to the differential of the ID, rate of change of ID with respect to LO. So in each of these diodes which are conducting, so you can write that as essentially the diode equation. You get IS from here. If you differentiate this one, you get IS times e to the power VDC over eta Vt times this lower the denominator here 1 over eta Vt. So this is the G diode, and that can be basically written as IS eta Vt over eta Vt times e to the power VDC over eta Vt. So that's equation number 1 we want to use later on. And the RF voltage now is basically the modulation, effectively the product of the G diode times the local oscillator voltage that is coming across into this particular diode, that is then appearing as VRF. So that is essentially proportional to the conductance of this diode times the voltage across it, in the AC voltage across it. So that's G diode VLOT. That you can write again as IS over eta Vt using 1 times e to the power VDC over eta Vt times VLOT. So you're adding this term to the G diode over here. So that's equation number 2. Now the basic diode equation is IDC is equal to IS times e to the power VDC over eta Vt minus 1. For large VDC you can much greater than the threshold voltage Vt, or the thermal voltage in this case, sorry. IDC is then approximately equal to IS in times e to the power VDC over eta Vt. So then you can basically take the log of each side, and you get VDC is approximately equal to eta Vt times ln IDC over Is. That's equation number 3. So from 2 and 3 you can combine 2 and 3, then you can just substitute for VRF. You get Is over eta Vt times e to the power eta Vt ln IDC over Is over eta Vt. So these two cancel out and equals, so this becomes again Is over eta Vt and IDC over Is times VLO. So again Is cancels out, and finally what you're left with is VRFT is proportional to IDC over eta Vt times VLOT. So we basically have proved that the RF voltage now is equal to the proportional DC current that is applied over here. So if you have no DC current, it means that you won't see any RF voltage, because ideally there's no asymmetry, there's no modulation of this conductance going on without this factor, the IDC doing all this, having an effect on this particular circuit. So with a zero IDC current, there is no leakage. An ideal RF mixer, fully balanced mixer. But as you start putting in a current, you'll start seeing that this voltage starts to increase as a function of IDC current. We like to prove this actually in a kind of an experimental setting which I can now try and do. And also you can simulate this effect actually if you have a fully balanced mixer, which you can do in, let's say, LT Spice or some simulator program, and prove to yourself that this actually happens as well. So here's my fully balanced mixer. It's the HP 10514A. If my thing will focus, you can see it. Okay, there you go. So on the L is my local oscillator, the X is going to be the IF, the DC current I apply into IF, and R is going to be my RF port, which I'm going to be observing on the spectrum analyzer. So, so you can see this is my connection to my spectrum analyzer, and then I got the RF signal coming into the yellow port over here, and I have this contraption to get the DC current from here, from this DC source into the X port or the IF port. So right now nothing is on. I'm going to set up the camera, and then we can look at some curves, some effect of the IDC changing on the spectrum analyzer levels, and we can start with zero current, and then we'll progressively increase the current to see how much it goes until eventually saturate, of course. Okay, so I've turned on the current. Actually, the current is off right now, and you have some basic leakage going on, even with nothing going on, no current applied, and that is at something like minus 58 dBm. So input is at 0 dBm at 50 megahertz, and what is leaking into the RF side is minus 58 dBm in that neighborhood with no current. So I'm going to slowly start increasing the current from around 10 microamps on this particular current source. And okay, so now it's 10 microamps. Really we don't see much of a change here. So let's track the peak here. So it's still at minus 60 odd dBm. Go to 100 microamps. So 100 microamps is a significant jump. So it's now up to minus 42 dBm at 100 microamps. And how much actually gets into the RF side depends on the characteristics of the diode and the losses, the conversion that happens. Basically we're talking about the conductance of the diode, how much that is a function of its properties and so on. So each diode that is there implemented in a fully balanced mixer will have different leakage, and this one is a fairly high frequency mixer, goes up to 500 megahertz. Okay, so we are at 100 microamps, and I'm going to go to 1 milliamp. So now definitely you see a lot more leakage into the RF port, and now it's at minus 22 dBm, and I think beyond, I think around 10 milliamps is not much of an effect, so I'm going to just slowly increase by 1 milliamp at a time. So this is 2 milliamps, it's now minus 17 dBm, 3 milliamps, minus 15.5 dBm, 4, it's minus 15, 5, minus 14.8, so it's saturating at this point, 6, 7, 8, 9, so at 9 it's minus 14.5 dBm, so it's not going to significantly increase too much. This particular mixer can take a maximum of 40 milliamps of current, so I can go up to the maximum over here and see what happens. So right now I'm at 9 milliamps, so let's go to 40 milliamps and see what happens. So this is now 10 milliamps, 20 milliamps, 30 milliamps, and 40. So at 40 milliamps we're still seeing something like 13 dBm, minus 13 dBm. So roughly out of the 0 dBm, minus 13 dBm is leaking into the RF, which is significant, of course. With no current, you can see it drops to minus 50, 55 dBm odd. So it's definitely this is a way of actually doing some attenuation of a signal without using any switching elements. You can use a current, DC current, purely a DC current apply into a LO port of a double balance mixer, and you can get fairly continuous tuning of that current. So this could be used in some circuitry where you think you need to modulate the amplitude of a signal that you want to have its amplitude controlled simply by applying a DC current. You don't have to do any like a reduction network or some divider networks or any course or anything that is discrete in nature. This can be a continuous time control that you can do with just a simple DC current into the LO port. So here's my simulation setup for the fully balanced mixer. Basically it's the same diagram I showed on the board, whiteboard, and this time I have a frequency of 3.5 megahertz signal going into the LO. The amplitude is 1 volt, basically 2 volt peak to peak, I guess, in this simulator, and applying it to the transformer shown over here, which is the primary side or the LO side of this thing, and then it couples into the secondary, which is tapped. So it's a 1-to-1 on each of these windings, and then go into this diode network, which is the 1N5818 diode. It's a Schottky diode, so has probably a low threshold, and typically they use such diodes for fully balanced mixers. And on the other side, on the RF side, you have the same thing, another transformer, 2 transformer windings coupling into a primary, which is again the same inductance that is used as 10 micro, and using this command called the K command, you can basically couple all of them together with a gain of 1. And on the IF side I have this current source. The polarity of the current really doesn't matter, because depending on which direction you put in, one of these pairs of diodes will turn on. And so right now this is a current going down into ground, and here we have the ground connection to the center tap. On the other side I have the RF side, which is currently disconnected from this. I put in a filter to show you the effect of filtering this output, because this is going to be distorted because of the fact that we are actually causing a DC current that shifts the operating point of these diodes and will cause even more nonlinearity, and hence the leakage into the RF port from the LO port. So if I run the simulation, I'm going to actually change this so I can get a larger range. Let's try 5 microamps to 5 milliamps, and I'm going to run this. Take a few seconds here. Okay, so now we have this family of curves which I swept from 5 microamps to 5 milliamps with 5 points per decade. So you have all these curves, and if I zoom in, you can see the distortion significantly distorted, as you can see. And you have when you have very low current, you have this very small signal. You have to zoom in to see that part, of course. So you can see it's still very distorted. So now if I run this with this filter connected, which is actually a tuned parallel RC LC filter, you will see that it's resonant at 3.5 megahertz, and hence you will actually see a big difference in that's the waveform over here. So let's look at that as it simulates through all these corners, these points, and zoom in again, and you can definitely see a change. It's sinusoidal at this point. That means it's pretty much removed all the harmonics, being a notch kind of filter with a very high Q, of infinite Q actually in this particular case. It will remove everything outside this in a very narrow band of 3.5 megahertz. So this is what you can actually do by just applying a DC current. You can modulate you'll attenuate the LO signal into the RF port, and you can use that as a means to drive some some other circuitry where you want to have variable amplitude at the same frequency that is coming in at the LO port. So one thing we can next look at is what is this look like as a function of current. So let's do that next. So this is the peak to peak voltage coming out of on this side of the RF side of the filter of the mixer as a function of the current over here. This is linear scale, so it looks kind of difficult to read this. There's no real information in terms of how it could be if you do it in a log scale, which becomes more interesting. So this is the log scale on the current axis, and now the log scale on the y-axis, or the output voltage. Now you can see that's actually very linear, and from the equation we saw that VRF was basically a linear function in this sense, in the logarithmic sense, because as every decade it basically goes up by a certain amount and until it saturates at a very high current, but below, in an ideal mixer you will have this going down the same slope all the way down to 0 effectively, or 10 to the minus something very small, never approaching 0, but you can see that it's very linear, and this is one good thing about a simulator. You can do all these kind of things and observe the behavior of these type of circuits. So at this point I think I can close this video. It's been pretty long. Hopefully this gives you some idea of using mixers for other functions, just purely mixing two different RF signals to get an IF. You can also do things like attenuation, which is a interesting thing I came across. I wasn't sure how it worked, and I was trying to understand it in a mathematical sense, and so I think this basically proves that there's some theory which matches what we see in real life, and also simulatable in SPICE and other simulators like these. So thank you for watching. Hope this was useful. Bye.